Interpreting the slope and the y-intercept. Like we said, the A is now your y-intercept or initial value, and then B is your slope, because we're using a model that looks like y equals A plus bx. The constants in the equation of the line give us important information about the relationship between the predicted y values and x. In the next examples, we'll focus on how to interpret the meaning of the constants in the context of the data. We'll look now at an example about body measurements. In the body measurement data collected from 21 female community college students, we found a strong positive correlation between forearm length, I guess this length here, from your wrist to your elbow maybe. The least squared regression line is here. Predicted height equals 39, so it's like y is your predicted height equals 39 is your value of A, plus your value of B is 2.7 times your forearm length, which is x. The equation tells us that to predict the height of a woman, start with 39 inches and add 2.7 inches for every inch of forearm length. The 39 is the predicted height of when x equals 0. Obviously, it does not have to make sense to predict the height of a woman with a 0-inch forearm length. This is an example of extrapolating outside of the range of data. Yeah, we only have data values that are positive forearm lengths. So we wouldn't even think about when x is 0. That wouldn't make sense. Regardless, 39 inches is the starting value in the least regression squares equation for predicting height based on forearm length. The value of B is a positive 2.7. This means that a 1.1 inch increase in forearm length corresponds to a predicted 2.7 inch increase in height. Another way to say this is that there is an average increase of 2.7 inches in predicted height when we compare women with forearm length of x to women with forearm length of x plus 1 inch larger. In the graph below, we see the slope B equals 2.7 represented by a triangle. An 8-inch increase in forearm length corresponds to a 21.6-inch increase in predicted height. The slope is the rate of change. B equals 21.6, the increase in height, divided by the x value, 8, the increase in forearm length, that's 2.7, the slope. An arrow points to the initial value as 39. This is the predicted y value when x equals 0. Now let's go ahead and scroll down and look at that. Okay, that looks exactly how described. The y-intercept is here, but that doesn't make sense in our example. But if you go out 21.6 inches in height, that'd be kind of crazy to think about. 21.6 inches taller than another person. That would mean that their forearm length is 8 inches taller. Now we're going to look back at that same example we saw before, highway sign visibility data. Recall that in a sample of 30 drivers, we see a strong negative linear relationship between the age of a driver and the maximum distance in feet at which the driver can read a highway sign Y. The least squares regression line is predicted y value equals the starting value plus the rate of change times x. But specifically, we found that the starting value was 576, and then the rate of change is a negative number because the distance you can see goes down as you age instead of going up. So it'll be minus 3 times your age. This equation is equivalent to what we wrote before. Predicted distance equals 576 minus 3 times the age, because adding negative 3x is the same as subtracting 3x. The equation tells us that to predict the maximum visibility distance for a driver, start with a distance of 576 feet and then subtract 3 feet for every year the driver's age. That's what this part tells us. The 576 is the predicted value when x equals 0. Obviously, it does not make sense to predict a maximum sign visibility distance for a driver who is 0 years old. This is another example of extrapolating outside the range of data. We obviously would not use this prediction. However, this initial predicted value is an essential part of the least squares equation for predicting distance based on age. The value of B is negative 3. This means that a 1-year increase in age corresponds to a predicted 3-foot increase in maximum distance at which a driver can read a sign. Another way to say this is that there is an average decrease of 3 feet in predicted sign visibility distance when we compare drivers of age X to drivers of age X plus 1.